Right, folks, we'll make a start. Like I say, we're trying out something new today to see whether or not this is a better way of engaging you with all the distance learning that you've got in chemistry. So this week I've set you some work on the halogens, which are in group 7 of the periodic table. I've given you a nice PowerPoint as well, but what I thought I'd do is to help you complete that piece of work, I'll do a little bit of a walkthrough and some teaching using the whiteboard behind me. So hopefully you'll find that useful. And this recording, like I said, yes, there are nice bird sounds. I've got the back door open. Thank you very much. But like I said, we're going to go through the halogens. Like I say, if you've already done the assignment, it'll serve as a good reminder for you. So let's have a look then. So group 7, the halogens. All right, so go back to my board behind me. So what do we know? They're in group 7. They're called the halogens. We'll talk about what that name means in a moment. But they've got 7 electrons in their outer shell, so they're not stable. So the key thing we need to know is that they want to gain 1 electron. So they want to gain electrons. This is different to group 1 that you looked at last week, because group 1 elements wanted to lose electrons. And there's a general rule there. Metals want to lose electrons to have a full outer shell. Non-metals want to gain electrons to have a full outer shell. So let's look at these things then. We've got fluorine, chlorine, bromine, iodine. They've all got one thing in common. They've got 7 electrons in the outer shell. So how do they actually exist? Well, if we have a look here, this is a fluorine atom. Yeah, so this is an individual fluorine atom. Now, would fluorine exist just as individual atoms floating around? No, because it doesn't have a full outer shell. But so how does it bond? How does it exist as an element? So you've got individual fluorine atom there, wants to gain an electron, and another individual fluorine atom there also wants to gain an electron. So what do? Well, if they both want to gain electrons, what they'll do is they'll share. Right, so non-metals, when they bond to each other, think back to our bonding work we did earlier this year, will want to share electrons. So what I'm going to do is I'm going to draw that, overlapping that. Make sure I've got 7 black crosses and 7 blue circles. And now when you count around each atom, does it have a full outer shell? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So now we've turned our individual fluorine atom, it's now called a molecule. So this is a fluorine molecule. And because all of these other elements have the same thing in common with 7 electrons in an outer shell, they must all exist as molecules like this. So fluorine exists as F2, chlorine exists as Cl2, bromine is Br2, iodine is I2. Okay, another big word I'm going to use here that you might see in some textbooks, you will do when you get to university as well, is that these molecules are diatomic. Okay, so they are diatomic molecules. So what does that actually mean? Well, di, like dialogue or dissect, means 2. Okay, and atomic means atoms. So these are basically 2 atom molecules, and a molecule is just something that's got a covalent bond within it. You might, rather than having to draw this out all the time, the shorthand way of doing it is using a stick diagram. So they're the individual atoms, and that is our covalent bond. So the covalent bond there is that shared pair of electrons. So that is a covalent bond. It's a single covalent bond. All right, and they exist as F2, Cl2, Br2, I2. No, it's not a Venn diagram. I've just seen a question there, but it does look like that. I do agree. So you've got F2, you've got Cl2, you've got Br2, and you've got I2. Okay, so like I say, if you want to make notes as you go through this lesson, please feel free. Like I say, I'll upload it to YouTube later so you can actually watch it back. So they exist as diatomic molecules. We've got F2, Cl2, Br2, I2. Okay then, well, let's have a look at what they actually look like at room temperature. Well, fluorine is a pale yellow gas. So fluorine is a pale yellow gas. Chlorine is a pale green gas. And like I say, I'm just going to underline the states of matter because that's quite important. Bromine is an orange liquid. And iodine is a black solid. So we can see a trend here. I don't have to put any numerical data up because we can see a trend in terms of their melting and boiling points. And hopefully you can see, just get rid of this bit here, that as you go down the group, you get increasing melting and boiling points. And let's discuss why that is. So why are the melting points getting bigger as we go from there down to there? Well, what's happening with the molecules? They're effectively the same. They've just got two atoms and a single covalent bond. So something must be changing about the molecules themselves. And what it's to do is it's to do with size. So the fluorine molecule would be the smallest because fluorine is the smallest atom. Chlorine would be slightly bigger. Bromine would be even bigger. And iodine would be the biggest. All right. And there is a general rule for the molecule, and this is really AS chemistry, but I think you guys can take it. The bigger the molecule, the stronger the intermolecular forces. I'm just going to write that down. Bigger molecule, stronger intermolecular forces. So what does that mean? So the bigger the molecule, the stronger the intermolecular forces. So again, let's look at this word here. Inter means between. Molecular means molecules. So the forces between the molecules. And hopefully you can see that would make sense. So you get more forces between two bigger molecules than you would between two smaller molecules. Therefore, the bigger the molecule, the higher the melting and boiling point. All molecules have lowish melting and boiling points. So even though this is a solid at room temperature, it will still melt and boil, although iodine is quite unique. It sublimes. It goes straight from a solid to a gas at a relatively low temperature. And that's because all intermolecular forces are weak. So think about water, for example, is a simple molecule. The forces between those molecules are weak. Carbon dioxide is a gas at room temperature that exists as molecules. The forces between those molecules are weak. Iodine exists as molecules. The forces between the molecules are weak. But the forces between these molecules are stronger than the forces between these molecules. And that's all to do with size. So the bigger the molecule, the stronger the intermolecular force, the higher the melting and boiling point. You would have seen this before when we looked at fractional distillation of crude oil. So you think about bitumen, really big molecules like 30, 40, 50 carbon atoms, very, very high boiling point. At the top of the fractionating column, you've got methane, which has got like one carbon atom in it. Right? It's very, very small. It exists as a gas at room temperature. So again, the bigger the molecule, the higher the boiling point due to the stronger intermolecular forces. Okie dokie. So let's move on then to have a little bit of a look at the reactivity of these things. So let's look at reactivity. I'm just going to get rid of this and then start looking at reactivity. I'm just going to draw two of the atoms here. So I've got fluorine, which has got 9 electrons. So I'm just going to focus on the atoms now rather than the molecules. So 9 electrons, 2 in the first shell, 7 in the second. Chlorine would be 2, 8, 7. So let me just draw those out. And chlorine. Okay, so there we go. Now, when we're discussing reactivity, last week you looked at the alkali metals and it showed you a couple of videos of sodium, lithium, rubidium, cesium, francium, rubidium and cesium being chucked into water. And they got more reactive going down the group because they wanted to lose electrons. Don't forget, these things want to gain electrons. So we need to have a little bit of a chat here. So if I've got two atoms here and there's one electron to be gained, which one of these is going to gain that electron more easily? All right, is the question. So how do we go about doing that? So let's think, which one of these, just think about yourself now, which one of these would be better at attracting that electron? So just think about an answer, and I'll give you about 30 seconds, and I'll go through it. Okay, so which of these would be better at attracting electron? The answer is actually fluorine. Fluorine would attract that electron more easily. Well, why would it attract electrons anyway? Well, electrons are negatively charged, and the nucleus of any atom is positively charged. And it's a bit of a question about distance, really. Look at the distance between the nucleus here and the outer shell. It's very, very short. Yeah, it's a very short distance. Compare that to chlorine, it's a bigger distance, therefore there is a weaker attraction to the outer shell. So the smaller the atom, the stronger the attraction between the nucleus and the outer shell. So the easier it is to actually gain electrons. So reactivity actually increases going up the group. So it's the opposite rules to the alkali metals, which got more reactive going down the group because they wanted to lose electrons. And the bigger the atom, the easier it is to lose electrons. Whereas fluorine and chlorine and bromine and iodine, they want to gain electrons. So it's the reverse trend. So why does it get easier to gain electrons? Well, smaller atoms. You get smaller atoms going up the group. Okay, so what does that mean? There is a stronger attraction between the nucleus and outer shell. Okay, so going up the group, you can see clearly just between these two diagrams here that fluorine is smaller. So the smaller the atom, that gives you 1 mark there. So it's a stronger attraction between the nucleus and the outer shell. So link it back to reactivity. What do these things need to do to become stable? They need to gain electrons. So I'm just going to put that in as my final point. So easier to gain an electron. Okay. So they get more reactive going that way. All right. Cool. Right. Just looking at some of the responses now to that. Yeah, see some of you got that, which is good. Thanks for noticing the personalized ADS tracked up. Okay, so that's the key thing with the halogens. They get more reactive going that way. In fact, fluorine on the periodic table, fluorine is the most reactive non-metal on the periodic table. So the general rule is that the closer a non-metal is to fluorine, the more reactive it will be. Looking at the metals, the other end of the periodic table, cesium and francium at the bottom of group 1 are the most reactive metals. So the closer a metal is towards cesium, the more reactive that metal is. That's a general rule. It works quite well at GCSE. Okay then, so let's have a look at some equations. Right then, let's show you these halogens reacting. So let's look at the reactions between, so we'll do sodium plus fluorine. Okay, what will that make? All right, well, it will make, so I'll put the word equation first, sodium plus fluorine will make sodium fluoride. Okay, so sodium plus fluorine makes sodium fluoride. So that's a key thing in terms of terminology. The halogens themselves, the group 7 elements, are enes: chlorine, fluorine, bromine, iodine. But when they react with something, they make ides, fluorides, chlorides, bromides, iodides. So again, your terminology is crucial here. Yeah. And the formula would be NaF. Well, why is that? Well, sodium is in group 1. Okay, so sodium is 281. Fluorine is in group 7, which is 27. So just having a look in terms of what happens here. Remember, how will they bond? Well, this is a metal, so it wants to lose 1 electron. This is a non-metal, so it wants to gain 1 electron. So what happens is the metal donates to the non-metal. And then what happens is this will become positively charged because it has lost an electron. This will become negatively charged because it has gained an electron. Yeah. And what would the ratio be of the ions in this compound? +1, -1. They're balanced. So it's NaF. So it's NaF. And then to balance this, okay, so balancing the equation is something very important in chemistry. How many Na atoms have I got here? 1. How many Nas have I got there? 1. So they're balanced. 2 fluorines here, only 1 there. So I need to double everything in there. But by doubling everything in that formula there, I actually need more sodium. So that is the actual equation for the reaction of sodium plus fluorine. And it makes sodium fluoride. And again, because you know that, you could swap fluorine for chlorine, bromine, or iodine. So if it was sodium plus chlorine, it would make sodium chloride. All right. Yes, that is a very naff joke. Thank you, Ashton. So, and by naff, I do mean awesome. Right. So we'll look at one more then. So we'll look at sodium chloride. Okay, and it balances in the same way as well. So once you know how to balance one equation between a group 1 metal and a group 7 halogen, it's just a 2:1:2 ratio. And what will these things look like? What do these salts at the end look like? Because that's what these things are called. These ionic compounds at the end are called salts. Yeah, salts. Basically are an ionic solid. So it's something made of ions, right? Usually in the reaction between an acid and an alkali, but not always, they're called salts. And that's where they get their name from, because halogens, halo, actually means salt. Okay, so it actually means salt. And gens, or gen, actually means genesis. So if you think about Genesis, or in terms of the Bible, it's sort of like beginnings, it's like creation. So it's like salt creator. And that's what halogens actually mean. So these things, when they react, fluorine becomes fluoride, which are salts. Chlorine becomes chlorides, which are salts. Bromine becomes bromides, which are salts. Iodine becomes iodides, which are salts. Okay, ionic solids, salts, and that's why they're called halogens. Okay, right then, last little bit, and then I'll take some questions. Right, let's have a look. So, reactivity. I'm just going to put my reactivity arrow back on. So, okay, and I'm going to make them back into their halogens. Okay, so more reactive going up. Okay. So I'm going to do a word equation first, and then we'll try and put similar equations as well, because you get something called displacement reactions. So displacement reactions, it's a very specific definition here. So what are displacement reactions? What does displacement mean? Displacement means basically replacement. So something is going to be swapped in these reactions. So it's when a more reactive halogen replaces a less reactive halogen in one of its compounds. Okay, so there's the sort of definition, if you like. And let's do a couple of word equations. Let's try and put this into practice. So we've got potassium bromide plus, and we'll just pick any one of these, chlorine. That'll do. Okay, so potassium bromide plus chlorine. Will we get a reaction? Okay. Well, let's have a look. What's the battle between? It's between bromide and chlorine. So the question is chlorine reactive enough to displace the bromide? Is it reactive enough to replace the bromide? Yeah. I'll let you answer that question in the chat. So is chlorine reactive enough to replace the bromide? If you think yes, what will it form? So I'm going to give you a bit of a chance now to answer the questions in the chat on this video. So any answers? Do you think that reaction will happen? And if so, what will it form? Niall, congratulations. That is absolutely spot on. Right, so he's put that it will form potassium chloride and bromine. Okay, and again, notice the language here. Potassium bromide plus chlorine makes potassium chloride plus bromine. So the chlorine replaces the bromide to make the chloride, and then bromine will be released. All right. So again, word equations, very important, and congratulations to anyone else who got that. All right. So let's have a look at the symbol equation for this. So you've got KBr plus Cl2 will make what? So have a go at that, all right? I'm not going to tell you the answer. I want you to think about it now. Have a look. What do you think the formulas of my products will be? So what will the formulas of my products be? And then can you balance it? Correct. Well done, Lacey. That is spot on. So we end up with KCl and Br2. Right? Fantastic. Well done. But has anyone balanced it? Is that a balanced equation? So I'm going to give you about 30 seconds now to write down the answer, but as a balanced symbol equation. Okay, so to balance it, is that a balanced equation? Yes or no? And if not, how would I balance it? Well, first things first, always balance the metals. So you've got K there, so you've got 1K there, 1K there, they're balanced. Do the BRs next if you want. So we've got 1 BR there. Yep. Oh, someone's got an answer in. Correct. Niles absolutely smashed it there. Well done. So he's created that answer there. Let's just go through the actual workings again. So there was 1K, 1K, 1 BR, but 2 BRs there. So I'm going to have to double everything in here. But by doubling everything in here, I've now got 2 Ks on this side. So there'll be 2 Ks on that side as well. And you might get asked as well, right, when you get to A level, more likely, but they could get asked this question on the higher tier at GCSE as well. What would you observe in this reaction? Well, what am I actually forming? I'm actually making these things here. I'm going to circle one of them, bromine. Bromine has been produced. So what would I see being formed? Well, if you look back to the start of this video, what did we say these things actually looked like as elements? Pale yellow gas, pale green gas, orange liquid, black solid. So if I'm getting bromine being produced, I'm going to see it look like an orange liquid. Yep. And what I'll do is I'm going to share you another couple of YouTube videos of people doing these reactions. You can see it happening later. So that's pretty much the whole of the halogens part that I wanted to discuss today. All right. If you have any sort of questions whatsoever, all right, put them in the chat now. I'll be around for another few minutes. And like you say, any feedback you've got on whether you found this to be useful, all right, let me know. If you think it's been a waste of time, also let me know. And I'll see if I can do any more if you found this to be useful. So any questions, just put them in the chat and then I can answer them whilst you're all online. Okay.